if I'm finding the dot product of two vectors, that means that I'm taking each of their components that are sitting in the same spot, right? So like my x component, y component, z component, or my I, j, k component. I'm going to multiply them together. So 1 times 0 plus 1 times -1 plus 2 times 1. And I think that should work out to 1 because it's a -1, +2. I get 1 as a value for that dot product. To find the magnitude or the length of A, that's coming from the square root of squaring each of the components and adding them together. So 1 squared plus 1 squared plus 2 squared, that's 4, 5, 6. So I've got the square root of 6. And then for B, that's going to look like the square root of 0 squared plus -1 squared plus 1 squared, or the square root of 2. So one of the things that we can do when we're looking at two vectors, one of those things we might be asked to do is to find the angle between the two vectors. Now, I don't really want to draw these in three-dimensional space, so I'm just going to draw pretend vectors. So my pretend vectors are going to look like A, and let's see which one was longer. Well, A was longer than B. So here's my pretend vector A and my pretend vector B. And if I want to find the angle between them, there's an alternate form for the dot product, and it actually comes from a geometry formula for the law of cosines. I'll be honest, I took geometry a really long time ago, and I'm sure even when I took it, my teacher did a fantastic job of explaining the law of cosines, but it did not stick with me for all these years. Luckily, the book has done the work for us and taken that law of cosines, rearranged the whole thing in the picture, and given us this nice, neat little package, which says A dotted with B is equal to the length of A, and I'm going to put my vector hats on because I can't draw a bold letter. Length of A times the length of B times cosine of the angle between them. So if I wanted to find the angle between A and B, I can use this equation and rearrange it until I get the theta by itself. So plugging stuff in here, my magnitude of A, or my length of A, was equal to the square root of 6. My length of B was equal to the square root of 2. Oh, I put that on the wrong side, didn't I? Sorry about that. Over here, we needed the dot product, and our dot product was 1. Length of A was square root of 6. Length of B was square root of 2. And then we have cosine of theta. Well, if I rearrange that equation, first of all, quick reminder, if I'm multiplying two things that are both square rooted, I can squeeze those together under a single square root. So that can be written as the square root of 12. So if I get the cosine by itself, then cosine of theta would be equal to 1 divided by the square root of 12. Now, I had a couple people email me questions about that, kind of along the lines of now what? So personally, I'm going to look at this and say 1 over the square root of 12, that is not a value that comes out of any of our nice trig angles, meaning pi over 6, pi over 4, pi over 3, pi over 2. That's 1 over the square root of 12 is not anything pretty that we're used to seeing pop out. So if I wanted to get the theta by itself, I'm using my trig skills to say getting the theta by itself, I would need to take the arc cosine or cosine inverse of both sides of this equation. And when I do cosine inverse of cosine, they're inverse functions, so they kind of undo each other. And I'm just left with theta is equal to cosine inverse of 1 over the square root of 12. Now, I have no idea what this is. That's the point where I pick up a, that was really loud. That's the point where I pick up a calculator and throw it at a metal object. That's the point where I pick up a calculator to figure out what cosine inverse of 1 over the square root of 12 is. When I grab that calculator, I'm going to be careful to make sure that I'm either in degrees or in radians, depending on how I'm supposed to put the answer there. Oh, totally. For the exam, could we leave it that way? Absolutely. We're going to walk away from that stuff. If I don't get a calculator, walk away. I only bring it up because I know that some of the textbook problems actually basically tell you to use a calculator to come up with the angle, but that is what we would have to do. Now, there are some times where what we get over here does come from one of our nice triangles, right? So if we had done this problem and this had all rearranged itself to get cosine is equal to 1 over the square root of 2, I'm going to go with that's an angle you're supposed to know. That means that theta is pi over 4. But you'll get the same answer whether you call that theta equals pi over 4 or you put into a calculator cosine inverse of 1 over the square root of 2. These are equivalent because they're answering the same question. So if I look at this picture, and I know I mentioned this on Monday, but if I think about drawing in a right triangle, then the amount of the vector B that is moving in the same direction as A, we call that length there the scalar component, or our book uses the term comp. That's the comp of B onto A. So that length right there, we can get using geometry if we really wanted to, or our newfound dot product-y skills. So if I wanted to know that piece right there, and I think about this triangle, right? I don't know what that piece is. I don't know what that piece is, but I do know the length of this side of the triangle. So if I kind of rotate that around in space, then there's that right angle, and I've rotated it all the way around. So that hypotenuse is the length of our B vector, and this side is what we're trying to find. So for the moment, I'll just call it X. So if I'm trying to find that side, and here's that angle theta, then in terms of trig functions, I know that the trig function that goes with these two sides is cosine. So looking at this, looking at that picture, I know that cosine of theta should be my adjacent over the hypotenuse, or X over that length of B. Since X was the thing I was trying to find, that tells me that X is equal to the length of B times cosine theta. And this is where we're going to get creative. Since I didn't really know what cosine, I don't really know what the angle between these two vectors is, but we have a relationship between cosine and our dot product. Because that's that same angle, that's the angle between A and B. That means that if I go back to that idea that A dot B is equal to the length of A times the length of B times cosine theta, then notice I've got that B cosine theta right here. So if I take the B cosine theta out of here, I can divide both sides just by the length of A. And then I'm left with B cosine theta. which means that missing side that we were looking for can be found by doing A dotted with B divided by the length of A. And our textbook gives that a special name and calls it the comp of B onto A, or the scalar component of the part of the vector V that is in the direction of the vector A. So this right here is our formula for the scalar component of B onto A. And for this particular problem, if I wanted to calculate it, I've already got what my A dotted with B is. So our comp of B onto A is equal to, our dot product was 1, and our length of A was the square root of 6. So there we go. That is our scalar component of B projected onto A, or of B onto A. Well, that scalar component means we looked for the length. But suppose I didn't really want the length, and I actually wanted to think about the vector that has the length that we're looking for, but a vector needs a length and a direction. So in order to give that vector a direction, I'm going to take that length that we just found, and I'm going to multiply it by the direction of the vector A. When we talk about the direction of a vector, that means we're taking the vector and dividing it by its magnitude, or making it a unit vector. So to get the vector projection, or we write this as PROJ, the projection of B onto A, we start with that scalar component, that A dotted with B over the length of A, and we multiply it by the unit vector of A, because that's going to give us the direction that we're trying to move in. And to find that unit vector, we'd have A divided by the length of A. The matrix is really just a way of organizing information. Now, it's a little bit different from like a table, which might be how we normally think about Excel. But if I draw a matrix and I put in, let's see, 2, 3, 1, 4, -1, 0. So to sort of make the analogy to an Excel document, in Excel, right, if I were looking at this, you'd have a grid there in your Excel or Google Sheets spreadsheet, and these things are called columns and these things are called rows. That's the same whether we're talking about it as a spreadsheet or we're talking about it as a matrix. So this matrix has 3 rows and 2 columns. And we talk about the dimension of the matrix as 3 by 2. So when we're giving the dimension or the size of a matrix, we always list the number of rows by the number of columns. That doesn't mean I'm multiplying those two things together. I'm not saying that it's 6. We read this as 3 by 2. We also have a way of designating or sort of numbering those rows and columns. So if I wanted to say, you should go look at the number 4. Well, if I think about an Excel spreadsheet, in Excel, these would be labeled as A, B, and 1, 2, 3, right? And so in Excel, you might reference B2, and B2 would tell you we're looking for that number 4. Now in math, we label these a little bit differently. And if I wanted to get to that element number 4, I might say something like A2, 2. And the reason for the 2, 2, oh, that was a terrible example. Let me pick another one. If I said A3, 1, that's equal to -1. So when we're talking about a location in a matrix for a number, it's always rows before columns. I had a teacher years ago who told me all matrices are Roman Catholic. So that's how I remember rows before columns, RC. So I've got RC, my third row, first column, and the element there is -1. Okay, so far none of that is particularly exciting. I mentioned on Monday that when we're labeling vectors, the common notation is to use lowercase letters. When we talk about matrices, we generally use capitalized letters. So if I called this matrix A, oh, and the other thing is, we don't really write those lines in. They're useful for kind of visually keeping track of stuff, but when we write a matrix, we just put all of the numbers in, kind of trying to be careful about the rows and the columns. So if I called this the matrix A, then the first thing that I want to talk about is all the kinds of sort of arithmetic that we could do with that matrix A. So if I wrote something like 5A, that means that I'm going to take each element in the matrix and multiply it by 5. So I'd end up with 2 times 5, 3 times 5, 1 times 5, 4 times 5, -1 times 5, and 0 times 5. That wasn't very exciting. Suppose that I have another matrix, B, and my matrix B is going to be equal to 1, 1, 2, 2, 3, 3. Again, if I wanted to look at the size of matrix B, it's 3 rows by 2 columns. So this is also a 3 by 2. What that means is that I can add or subtract A and B because they're the same size. So when we're adding and subtracting things, we can only add and subtract things that are the same size. The way I kind of like to think about this is if I had x squared plus 3x squared, they're kind of the same like size of x, they're the same dimension of x because they're both an x squared. So I can combine those together. But if I had an x squared and a 3x, those aren't the same kind of dimensions. So I wouldn't be able to combine these pieces together. For matrices, what that looks like is if I take A plus B, that addition works probably exactly the way you're thinking. I match up each of the components and add them in place. Since 2 is in the first row, first column, and 1 is in the first row, first column for B, then my first row, first column here looks like 2 plus 1. And then I'd have 3 plus 1 for my first row, second column entry. For my second row, first column, I'd have 1 plus 2. And then 4 plus 2. -1 plus 3, and 0 plus 3. And I'll go ahead and change that 2 plus 1 over here to be a 3. And we could do the same thing with subtraction. If I had A minus B, then I would take each element of A and subtract the corresponding element from B that's living in the same space. Well, if I can add or subtract matrices, what usually comes next in our arithmetic class? Multiplication. Here's where life gets messy. Okay. Matrix multiplication doesn't work at all the way you want it to. Sorry, that's just the reality. But matrix multiplication is kind of going to form a foundation for some things that we're going to do later. So it's super important that we get good at that matrix multiplication early on. So here's my matrix A, and I said that this matrix is a 3 by 2 because it has 3 rows and 2 columns. So when we're adding and subtracting matrices, I need them to have exactly the same dimensions. But when I'm multiplying matrices, in general, they're not going to have the same dimensions, but they do have to have a very specific relationship. So I can take that 3 by 2 matrix and multiply it by a 2 by 2 matrix. And I'm going to make up a 2 by 2 matrix here. Let's go 4, -1, 1, 2. Sure, why not? So the way the matrix multiplication works, if I line up my 2 pieces, and I'm calling this now, this is my matrix A, and here's my matrix B. When I put them in order, and I write out their dimensions, these, what I'm calling those inner dimensions, they have to be the same. And the outside dimensions tell me how big the answer will be. So when I multiply a 3 by 2 times a 2 by 2, I check that these 2's that are next to each other are the same. They are. And now I know the answer is going to be a 3 by 2. I'm giving myself lots of space for a reason. That's maybe not quite enough space. So my answer here is going to be a 3 by 2. I'm going to do this first multiplication problem kind of in slow motion. Once you've done a dozen of them, it'll start to click and it'll feel better. But for now, I'm going to lay this out. So if this is going to be a 3 by 2, that means 3 rows, 2 columns. So I'm just going to give myself placeholders for 3 rows set into 2 columns. And the next part that I'm going to do, and I wouldn't do this like after you've got the multiplication stuff, these steps that I'm doing, you probably wouldn't write out. I'm just writing them out to show it the first time. So if I pick a piece here, right? So if I pick, thinking about Excel, if I pick this cell is in the second row, first column. So I'm going to write that as row 2, column 1. And the way that I'm going to get the answer here for the multiplication problem is I'm going to take row 2 of the first matrix and multiply it by column 1 of the second matrix. I'm going to come over here and I'm going to take row 2 and multiply it by column 1. And when I say multiply it by, we're actually technically doing a dot product. Remember, with our dot product, we multiply the components together and add between components. So I'm going to take the first component times the first component, so 1 times 4. And I'm going to add that to my second component times my second component, 4 times 1. Let's do another one. This piece is in my third row, second column. So this is my row 3, column 2. So to get this answer, I'm going to come over here and I'm going to take row 3. So row 3 from my first matrix and multiply by column 2 of my second matrix. So to get what goes in here, I'm going to end up with -1 times -1 plus 0 times 2. Well, I'm just 0 because it's 0 times 2. And we can keep going and get all of that done. Now, if you're sitting here thinking, thought I was in a calculus class, why are we doing arithmetic? Cool, we're going to get back to the calculus, but we have to get good at this matrix stuff in order to move on to the fun stuff. And by Friday, I'm hoping we can talk about some of the fun stuff. But for now, just know that when you're doing matrix algebra, it really is a lot of arithmetic. Take your time with it. Make sure you're getting your numbers right. So I do want to finish off this multiplication. So I want to get all of these filled in here. So this right here is row 1, column 1. So I'm going to take row 1 of my first matrix times column 1 of my second matrix. Oh, how do you know that? Great question. How do I know where all the things go? Yes, totally. So really, I'm using my Excel skills here. So I'm thinking about and remembering that all matrices are Roman Catholic, R before C. So if I want to know what spot this is, I'm going to count down the number of rows. So row 1, row 2, row 3. So this is in row 3. And I'm going to count over the number of columns, but this is in my first column. So this is row 3, column 1. Now there is something kind of annoying about the English language, and that is, like, let's say that we were in a classroom. I know it's hard to remember what that was like, but let's say that we were in a classroom and there were a bunch of desks around, and those desks were arranged in a grid in the room. In the English language, we actually would call this a row and this a row. It's kind of annoying. And so what is important is that mathematically, rows in a matrix mean that we're counting off those horizontal pieces, and columns mean we're counting off the vertical ones. Again, just to sort of like help get the hang of it, columns would help hold up a building. And so these are my columns because they would help hold up the building. So they've got to be vertical. I don't know if that helps, but I'll just keep going. So this right here, I have to figure out the row first. So if I'm counting the rows, this is in my first row, and then I'll count over my columns. That's column 1, column 2. So this is row 1, column 2. This is row 2, column 2. And you don't have to write any of that out. I just think that it helps when you first start doing the matrix multiplication, just to keep track of it all. Okay, back here. So if I'm finding the entry in row 1, column 1 for the multiplication, I need row 1 times column 1. 2 times 4 is 8. And 3 times 1 is 3. So I'll just write that as 8 plus 3. Here, row 3, column 1. Row 3, column 1, I'll have -4 plus 0. Row 1, column 2. Row 1, column 2. -2 plus 6. And row 2, column 2. Row 2, column 2, -1 plus 8. So my final answer for A times B would be the matrix that looks like 11, 4, 8, 7, -4, 1. There are a ton of matrix calculation tools out there on the internet. I posted a link to one of them in our Canvas shell under the modules. And what I want to do is I want to calculate 2a minus 3b. Just like if we went back in time to maybe your pre-algebra class or something where we were talking about order of operations, we're going to do order of operations all over again here. So that's that PEMDAS thing, but multiplication is going to come before the subtraction. So that means if I wanted to compute this quantity, I should first find 2 times that A matrix and 3 times the B matrix. So 2 times A, I'm going to multiply each of the entries of the matrix by 2. And then we're going to be subtracting off, multiplying each of the entries of B by 3. So I'll have 3, negative 3, 0, positive 3. And then when we do the subtraction, so first of all, we should do a quick check. This is a 2 by 2 and this is a 2 by 2. And apparently I can't do arithmetic because 3 times 2 is definitely 6. Thank you. So 2 by 2 minus a 2 by 2, we're good to go. When we do that subtraction, nothing weird happens. I would say it just does what we think it probably ought to do. So because that 6 and that 3 are both sitting in row 1, column 1, I'm going to subtract those entries. So 6 minus 3, I get 3. The 0 and the negative 3 are both sitting in row 1, column 2. So I'm going to take 0 minus negative 3 and get a positive 3 back. The 4 and the 0 are both sitting in row 2, column 1. So I'll have 4 minus 0 and get 4. And for my last set of entries here, in row 2, column 2, I'll have 10 minus 3. Yay! There's my subtraction. Just for fun and to practice multiplication, let's multiply A times B. Oh, actually, we should do something else. We're going to calculate B times A. Now, when we're multiplying numbers, if I multiply 6 times 3, that's the same result as multiplying 3 times 6. That doesn't work for matrices. Weird, right? Matrices, matrix multiplication is not commutative. We can't switch the order and get the same answer. Let's show that. Hopefully I've chosen random enough matrices that nothing weird happens. So if I calculate B times A, that means I'm doing 1, negative 1, 0, 1 times 3, 0, 2, 5. So let's do a quick check to see if the dimensions will work out. So that's 2 by 2, and that's a 2 by 2. My inner dimensions are the same, so my outside dimensions tell me that my final answer should be a 2 by 2. And I'm going to give myself sort of the same markers here, but this time I'm going to do more of the arithmetic in my head. So this entry is in row 1, column 1. So I'm going to take row 1 times column 1. So I'll have 3 plus negative 2. This entry is in row 2, column 1. So I need row 2 times column 1. I'll have 0 times 3 plus 1 times 2. This entry, I'm in row 1, column 2. So I need row 1 times column 2. I'll have 1 times 0 plus 5 times -1. Last, I've got row 2, column 2. Row 2, column 2. 0 times 0 plus 1 times 5. Just for fun, let's calculate A times B. And since they're kind of already lined up together, I'm going to go ahead and just roll with it and not write them all over again. But I'm going to give myself my 4 boxes to keep track of my numbers. Here, that's, sorry, row 1, column 1. So I need row 1 times column 1. I'll have 3 times 1 plus 0 times 0. Well, already that's enough to say these are not the same matrix, but I'll keep going. Row 1, column 2. Row 1, column 2. 3 times -1 plus 0 times 1. Here, I'm in row 2, column 1. So I need row 2, column 1. Got 2 times 1 plus 0 times 5. And last, this guy is in row 2, column 2. So I need row 2, column 2. 2 times -1 plus 5 times 1. That's 5 plus -2. That's a +3. So I think you can see these are definitely not the same matrix. In general, A times B does not equal B times A with matrices.